Hello everybody, welcome to another problem solving session. I'm going to work through the problems we looked at in class this morning dealing with series and parallel circuits. They are mowing the grass outside my office, so hopefully that noise is not too much on the video here. But here goes. Problem number one we looked at, say 4 resistors are wired to a power supply. Compute the equivalent resistance of the network in the figure, and it parenthetically tells us the battery has negligible internal resistance. What is the current through the 3 ohm resistor and what is the current through the 12 ohm resistor? Well, in this picture, they're again using this EMF symbol to symbolize, hey, we're always going to treat this as a perfect 60 volt battery that has no resistance to it. All right, so the first step in working out equivalent resistance is to look at the circuit and identify resistors that you can identify as being either in series or in parallel with one another. Recall that series requires the same amount of current to go through 2 resistors, and parallel means the same potential difference is established across 2 resistors. And in this circuit, there are 2 pairs initially of parallel circuits. This 3 ohm resistor is in parallel to this 6 ohm resistor because, again, I can connect one end of the 3 ohm resistor to one end of the 6 ohm resistor, and then the other end of the 3 ohm resistor to the other end of the 6 ohm resistor without passing through any other circuit element. So if I measured the potential difference across either of these resistors, they would match. Similarly, the 12 ohm resistor is in parallel to the 4 ohm resistor. So I'm going to redraw this circuit, but reduce the number of resistors down to 2. And each of those 2 resistors will represent the equivalent resistance of the parallel networks we just identified. So this is still a 60 volt battery. But to get these resistances, I need to sum find the equivalent resistance for 2 in parallel. So 1 over the equivalent resistance of any network is 1 over the first resistor plus 1 over the second resistor, and you can continue that if you have more than 2. So 1 over R1 plus 1 over R2. That means that the equivalent resistor for the first network, the 3 and the 6 ohm resistor, would be 1 over 3 ohms plus 1 over 6 ohms, and you take the inverse of that. You can do this on a calculator, but 1 over 3 is the same as 2 over 6. 2 over 6 plus 1 over 6 is 3 over 6. And then you got to invert that to have 6 over 3. That tells us the equivalent resistance of that first network is 2 ohms. So I'm just going to write that value for equivalent resistance in. And then do a second calculation for the other network. That equivalent resistance is 1 over 12 ohms plus 1 over 4 ohms inverted. 1 over 12, common denominator would be 12, so this would be 1 over 12 plus 3 over 12 would be 4 over 12. The inverse of that is 12 over 4, or 3 ohms of resistance. So this circuit is electrically equivalent to the first circuit, and it would contain a 2 ohm resistor and a 3 ohm resistor. Now, these two are 2 resistors that are in series with one another. So to figure out the equivalent resistance of 2 that are in series, I just sum those resistances. So 2 ohms plus 3 ohms is 5 ohms. And we can draw the final version of this circuit, which we've reduced to a simple circuit of 1 battery, 1 resistor. And we have the equivalent resistance here, which is 5 ohms. So that's our answer to A. The equivalent resistance for the entire circuit is 5 ohms. Part B of the question asks, what is the current through the 3 ohm resistor? And we have to be a little careful because there's a 3 ohm equivalent resistor right here. But they're actually asking us about the original 3 ohm resistor back in the original circuit. Well, once I've worked down to this step, I use Ohm's law to work my way back up to the original configuration of the circuit, figuring out things along the way. So, for example, I have a 60 volt battery and a 5 ohm resistor. And if you apply Ohm's law at that step, we would say that the current through this circuit would equal the potential difference across the resistor divided by that resistor. So that is 60 volts divided by 5 ohms. That's 12 amps, which would mean there would be a 12 amp current going through this resistor. There would also be a 12 amp current going through here and a 12 amp current going through here, because these are 2 series resistors that are equivalent to this 5 ohm resistor. And if I know that that's 12 amps, I can then apply Ohm's law to figure out what the potential difference across those resistors must be. So if we measured the voltage difference from here to here, it would equal the voltage difference rather from Ohm's law equals the current times the resistance. So the potential difference here would be 24 volts, 12 times 2. And the potential difference across here would be 36 volts. And I can check my work. 24 and 36 adds up to 60, which is the battery. So now I know everything in this middle circuit, and I go back up to this equivalent circuit right here, and I say, okay, if it's 36 volts across there, that 36 volts must still be the voltage across here. Because again, this 4 and 12 resistor in parallel are equivalent to my 3 ohm resistor here. Similarly, the voltage across this other network is 24 volts. And now if I apply Ohm's law and say current equals voltage divided by resistance, that is going to tell me that the current through this resistor right here is 24 volts divided by 3 ohms, or 8 amps. And the current through the 6 ohm resistor is 24 volts divided by 6 ohms, which is 4 amps of current through there. Similar kinds of reasoning, 36 volts across a 12 ohm resistor is going to produce 3 amps of current, and 36 volts across a 4 ohm resistor is going to produce 9 amps of current. And I think we now have enough information to answer all the pieces of this question, but we can check ourselves using some Kerkhof reasoning. So we worked out that there's 12 amps getting pumped by the battery in this circuit. 12 amps in the original circuit would get to this point. It would need to, at this junction, split into 2 currents whose sum is still 12, and that checks out. I still have 8 and 4. Comes back together and forms 12 amps right here in the middle. Then that's got to split in, again, 3 and 9 add up to the 12, so that all works out. Similarly, I can apply the voltage loop rule and say I increase by 60 volts going through the battery. And then whichever path I take here, I decrease by 24 volts and decrease by 36 volts to get back to where I started from voltage-wise. So with that information, we can write down our answers to B. What is the current through the 3 ohm resistor? That is 8 amps of current. And what is the current through the 12 ohm resistor? That is 3 amps of current. Now, I've showed you the formal way to calculate all of this stuff, but there are ways that you can reason about some of these problems, especially if there's a situation like this where the numbers are fairly easy to do the math with. The argument would go, I can get down to this point and figure out there's 12 amps of current. Well, when 12 amps of current gets here, this path with 3 ohms of resistance is half the resistance of this path with 6 ohms of resistance. And so if this path has half the resistance of the lower path, 2/3 of the current is going to take the upper path, and 1/3 of the current is going to take the lower path, and that'll allow you to split the current into 8 and 4 directly if you can think through that kinds of reasoning. Similarly, when you're at this junction, the lower path has 1/3 of the resistance of the upper path, so 1/4 of the current ends up going in the upper path, 3/4 of the current ends up going down in the lower path, 3 times as much current. And that's where I get the 3 and 9 as well if I want to use that kind of reasoning. So you don't have to formally do all of the Ohm's law calculations, but knowing how to do those Ohm's law calculations can be helpful, particularly in situations where there's not such quote-unquote nice numbers for the pieces of that circuit. Second question is pretty similar. But there's a subtle difference in the way these resistors are connected. There's no middle branch right here. So initially in this circuit, where I have 4 resistors, the 1 and the 3 ohm resistor in the upper branch are in series with one another, and the 7 and the 5 in the lower branch are in series. So just like I did last time, I'm going to redraw this. I now have a 48 volt battery. But I'm going to redraw this into a circuit diagram that just has 2 resistors. And work out what those resistances are. Well, again, when you have series resistance, you sum directly. So that top one is just 1 ohm plus 3 ohms. So that's 4 ohms of resistance. The bottom branch is 7 ohms plus 5 ohms for 12 ohms of resistance. So let's label these values on our intermediate circuit. 4 ohms here, 12 ohms in the bottom. And now I have 2 resistors, and these 2 are now in parallel to each other again because they would have the same voltage measured across them, or you can connect ends of those resistors directly to the ends of the other resistor without passing through other circuit elements. So I'm going to, at the end here, draw an equivalent resistance, equivalent circuit rather, that has just a single resistor in it. So here is my 48 volt battery. Here is my resistor, and to find that equivalent resistance, I have to use the rule for summing parallel resistors, so I sum the inverses, so 1 over 4 ohms and 1 over 12 ohms, and then invert that. Again, we did this last time, but the common denominator is 12, so 3 over 12 plus 1 over 12 is 4 over 12. Invert that, you have 12 over 4, or 3 ohms. So there is a 3 ohm resistor, and that is in fact the equivalent resistance for the entire circuit, which answers question A. Question B wants to know how much current is going through this 3 ohm resistor. Again, not the equivalent 3 ohm resistor, but the original 3 ohm resistor, and how much current is going through the 7 ohm resistor. So similar to what we did last time, I'm going to apply Ohm's law down here and figure out how much current is going through this resistor. So current is a potential difference divided by a resistance. If I take 48 volts divided by 3 ohms of resistance, I find that's 16 amps of current. So I have 16 amps of current flowing through the circuit, meaning the battery is pumping 16 amps of current in all of these circuits because they're all equivalent to one another. And so you can proceed a couple of ways when you get back here to this step. Again, I'll do the formal calculations. There's 48 volts of potential difference across both of these resistors in the equivalent circuit. So I can figure out how much current that would be in each of those cases. I through the 4 ohm resistor is going to be 48 volts divided by 4 ohms of resistance, which is 12 amps. And the current through the 12 ohm resistor is going to be 48 volts divided by 12 ohms, which is 4 amps. So let's add that information on our diagram. I got 4 amps taking this path, and I have 12 amps taking the upper path. Alternately, you can use the same kind of reasoning that we used at the end of the last problem. I got 16 amps overall in the circuit. When I get to this point, these two branches have differing amounts of resistance. The lower branch has 3 times as much resistance. So its current is going to be 1/3 of the current that goes through the top. So that ends up being 1/4 of the total current, 4 amps. The top ends up being 3/4 of the total current, or 12 amps. That means that when we get back up to this picture, there must also be 12 amps going through the top branch here, and 4 amps going through the lower branch here, and that is enough information to solve the rest of the problem. B asks how much current's through the 3 ohm resistor. Well, these two are in series with one another, so 12 amps goes through the 1 ohm resistor as well as the 3 ohm resistor, and the current through the 3 ohm resistor is 12 amps. And how much current's going through the 7 ohm resistor? That must be the 4 amp current. The third problem we looked at in this sheet was a little bit different. It is going to ask us to recall some information about power and revisit that concept. And a little bit different in the approach, because here I only know the value of one of my resistors. I don't know what the other two in fact is. That's what I'm tasked to do here. I can't then use my rules to directly sum these resistors immediately. But if you look, I do have 3 resistors that are parallel to one another. Again, you can connect one end of each of these resistors to the other resistor without passing through other circuit elements, so they're all going to have the same voltage across them. And indeed, whatever voltage they have across them is going to equal the voltage of the battery. And that should be enough to allow us to answer the questions here. Now, I'm just going to redraw this larger so that I have a big circuit diagram I can label things on as I deduce different pieces of this circuit. So again, we have 3 resistors in here. I have a battery, but I don't know what the battery's EMF is. I do know that I have 3.5 amps of current at that point in the circuit, and I have 2 amps of current here, which must mean, by the way, I also have 2 amps of current here and 2 amps of current here. I don't know what the resistance is here. It's just an R1. I don't know what it is here. It's R2. But I do know that this is a 10 ohm resistor. All right, so basically I've just recopied this diagram, given myself a little bit more space to label things. And so the first step is I want to find what R1 is. To To figure out what R1 is, I have to take advantage of the fact that I'm told R1 is dissipating electrical energy at the rate of 20 watts. So recall from previous discussion we said electrically power is a potential difference times a current, or a potential difference squared divided by a resistance, or current squared times the resistance. And the one that's going to be the most useful for us here is we know power and we know current and we don't know resistance, but that's what we want. So I'm going to take that third one. Power equals current squared times resistance, and solve for resistance. Resistance is going to equal power divided by the square of the current. So if I plug in my numbers, that is 20 watts over 2 amps of current squared, or 4, and that works out to be 5 ohms. So R1 is 5 ohms, and we figured out piece number 1 here. I'm actually going to answer question C next, because that, at least in my head, makes more logical sense to me. I've got 5 ohms of current here, and 2 amps, 5 ohms of resistance rather, and 2 amps of current going through here. So if I put my voltmeter right here, what am I going to read for a potential difference across this resistor? Well, there you can use Ohm's law, and voltage equals current times resistance, so 2 amps times 5 ohms is going to be 10 volts. But if I measure 10 volts across this resistor, it's in parallel to R2. That's going to mean it's 10 volts across R2. And it's going to mean 10 volts across the 10 ohm resistor, which means ultimately it's going to be 10 volts across the battery. So C, the EMF of the battery, must be 10 volts. Now let's go back and find R2. In order to get R2, you have to think about this first branch where we actually know the resistance. It's 10 volts across here, meaning it's also 10 volts across this resistor. And if that's the case, you can apply Ohm's law and say 10 volts across a 10 ohm resistor means the amount of current that's going down through this branch must be 1 amp. So if there's 3.5 amps coming here and 1 amp peels down in this branch, that means in this part of the circuit there's 2.5 amps. I'm applying my Kerkhof junction thinking right here. 2.5 amps that comes here. I know 2 amps leaves and goes here, which must mean there is 0.5 amp of current going down through R2. And again, I can use Ohm's law in this branch and say if I have 0.5 amp for current and a voltage of 10 volts, that must mean that R2 is 5 ohms, because R is a potential difference divided by current. Whoop, not 5 ohms, 20 ohms rather. So 10 volts divided by 0.5 amp of current would give me 20 ohms. Or I can use the kind of relationship reasoning I used on previous problems. For example, if I have a 10 ohm resistor and 1 amp of current goes through it, how much resistance do I have with 0.5 amp? Well, it's got to be twice as much resistance if I get half as much current. Finally, find the current through the R2 resistor. Well, we sort of did that coincidentally along the way. I through the R2 ended up being 0.5 amp of current, and now we know pretty much everything in the circuit. We know that the battery is 10 volts. It pumps out 3.5 amps of current. 1 amp goes through the 10 ohm resistor and has a potential drop of 10 volts. 0.5 amp goes through a 20 ohm resistor and has a drop of 10 volts. And 2 amps goes through a third resistor here, 5 ohm resistor, and again has a potential difference of 10 volts across that resistor. The last problem on this problem set Number 4 reads, consider the circuit shown in the figure. The current through the 6 ohm resistor is 4 amps in the direction shown. So what is the current through the 25 ohm resistor? And what is the current through the 20 ohm resistor? Now, you absolutely could, in this particular situation, since all the resistors are known, work out what the equivalent resistance of this circuit is. But it turns out that's not going to be super helpful for answering this particular question. So again, I'm going to try to turn this into a larger circuit diagram so we can label all the stuff as we figure it out walking through this circuit. This branch. All right, and we know, let's see what, 8 ohm resistor, 6 ohm resistor, 25 ohm resistor, and 20 ohm resistor. All right, we know 4 amps of current goes here. So I'm going to apply my Ohm's law thinking and say, okay, Ohm's law says potential difference equals current times resistance. So if I do 4 amps times 6 ohms, that is 24 volts of potential difference across here. 8 ohms is in parallel to the 6 ohm. Again, you can connect both ends, and that means the voltage across this 8 ohm resistor is the same as the voltage across the 6 ohm resistor. That's 24 volts. And if you do 24 volts divided by 8 ohms, you can reason that the current through this branch must be 3 amps. So 3 amps coming up to this junction and 4 amps coming from the top branch would combine and give you a current of 7 amps going through that 25 ohm resistor. If you have 7 amps going through a 25 ohm resistor, again, Ohm's law tells you that the potential difference across here is 25 times 7, or 175 volts. If you now apply your Kerkhof loop rule thinking, you can say, okay, if I start here, I go up by some potential difference of the battery, and I don't know what that potential difference of the battery is, but then if I follow this path, I'm going to go outer perimeter the whole way. I go down by 24 volts, and I go down by 175 volts, and then I'm back to where I started. That's telling us that the EMF, or the voltage, the theoretical voltage maximum of the battery, is 175 plus 24, so that's a 199 volt battery. Okay, we know then, of course, that the potential difference across the 20 ohm resistor must also be 199 volts, because it is directly connected to the battery. It's in parallel with this whole network up at the top here as well. And if you apply the thinking to that, 199 volts over 20 ohms means the current here is that lovely round number, 199 over 20 amps, which is almost 10 amps of current. And I believe we've figured out everything in the circuit, and we have enough to answer our 2 questions. What is the current through the 25 ohm resistor? Current through the 25 ohm resistor is 7 amps. And B, what's the current through the 20 ohm resistor? And that ends up being 199/20ths of an amp, which is just about 10 amps of current. So those are the problems we worked on series and parallel circuits. They link to the kinds of questions you will see on problem set 6 on Mastering Physics. And as always, if you've noticed an error in my solutions as I work my way through here, I would appreciate you letting me know about that. Thank you.